I'd like to talk now about some of the other cases that can occur because they lead to completely different pictures, which you should understand. So let's look at the case where our governors behave a little more badly, a little more combatively, or I don't know, whatever the word is. Okay, so it's x prime equals -1, negative x as before, but this time a firm response by Massachusetts to any sign of increased activity by stockpiling of advertising budgets. So here it will be, let's say New Hampshire now is even worse. 5 times we will quintuple whatever increase Massachusetts makes. We are not of course they don't have an income tax, but I don't know, they'll manage. -3y as before. Okay, what now is, let's again calculate quickly what the characteristic equation is. So our matrix is now -1, 3, 5, and -3. The characteristic equation now is lambda squared, what is that? Again, plus 4 lambda, but now the determinant is 3 minus 15 is -12. And this, because I prepared very carefully, all eigenvalues are integers, and so this factors into lambda plus 6 times lambda minus 2. Does it not? Yes. Right? 6 minus 12, 6 lambda minus 2 lambda, 4 lambda. Good. So, what do we got? Well, first of all, we have our eigenvalue lambda -6, and the eigenvector that goes with that is -1. So this is -1 minus -6 makes, shut your eyes, 5. So we get 5a1 plus 3a2 is 0. And the other equation, I hope it comes out to be something similar. I didn't check. I'm hoping this is right. So the eigenvalue, the eigenvector is, okay, now you've been taught to always make one of them 1. Forget about that. Just pick numbers which make it come out right. So I'm going to make this one 3, and then I'll make this one -5. As I say, I have a policy of integers only. I'm a number theorist at heart. That's how I started out life anyway. Okay. So there we've got a data from which we can make one solution. How about the other one? The other one will correspond to the eigenvalue lambda equals 2. And this time the equation is -1 minus 2 is -3. So it's -3a1 plus 3a2 is 0. And now the eigenvector is 1, 1. Okay, now we're ready to draw pictures. We're going to make the similar analysis, but it'll go faster now because you've already had the experience of that. So first of all, what's our general solution? It's going to be C1 times 3, -5, e to the -6t. And then the other normal mode will be, times an arbitrary constant, will be 1, 1 times e to the 2t. I'm going to use the same strategy. We've got our 2 normal modes here from which the eigenvalue solutions, eigenvector solutions, from which by adjusting these constants we can get our 4 basic solutions. So those are going to look like, let's draw a picture here. And again, I'll color code them. Let's use pink again. Pink, orange. Okay, so the pink solution now starts at 3, -5. That's where it is when t is 0. And because of the coefficient -6 up there, it's coming into the origin. Looks like that. And its mirror image, of course, does the same thing. That's when C1 is -1. How about the orange guy? Well, the orange guy now, when t is equal to 0, it's at 1, 1. But what's it doing after that? As t increases, it's getting further away from the origin because the sign here is positive. E to the 2t is increasing. It's not decreasing anymore. So this guy is going out. And its mirror image on the other side is doing the same thing. Now what we have to do is fill in the picture. Well, you fill it in by continuity. The nearby trajectories must be doing what similar things. So if I start out very near the pink guy, I should stay near the pink guy, but as I get near the origin, I'm also approaching the orange guy. Well, there is no other possibility other than that. If you're further away, you start turning a little sooner. So I'm just using an argument from continuity to say the picture must be roughly filled out this way. Maybe not exactly. In fact, there are fine points, and I'm going to ask you to do one of them on Friday for the new problem set, even before the exam, God forbid. But I want you to get a little more experience working with that linear phase portraits visual, because it's, I think, one of the best ones this semester. You can learn a lot from it. So anyway, you're not done with it, but I hope you've at least looked at it by now. Okay, that's what the picture looks like. First of all, what are we going to name this? In other words, if you just forget about the arrows, if you just look at the general way those lines go, where have you seen this before? You saw this in 1802. What was the topic? You were plotting contour curves of functions. Were you not? What did you call a contour curves that formed that pattern? A saddle point. You call this a saddle point because it was like a saddle, the center of a saddle, or it's like a mountain pass. Here you're going up the mountain, say, here you're going down, the way the contour line is going down. And this is sort of a minimax point. A minimum, a maximum if you go in that direction, and a minimum if you go in that direction, say. So without the arrows on it, it's like a saddle point, and so the same word is used here. It's called a saddle. You don't say point in the same way you don't say a nodal point. It's the whole picture, as it were, that's the saddle. It's a saddle. It's not, there's the saddle. There's, giddy up, but this is where you sit. Now, should I call it a source or a sink? I can't call it either because it's a sink along these lines. It's a source along those lines. And along the others, it starts out looking like a sink and then turns around and it starts acting like a source. So the words source and sink are not used for a saddle. The only word that's used is unstable, because definitely it is unstable. If you start off exactly on the pink lines, you do end up at the origin. But if you start anywhere else, ever so close to a pink line, you think you're going to the origin, and then at the last minute, you're zooming off and out to infinity again. So this is a typical example of instability. Only if you do the mathematically possible but physically impossible thing of starting out exactly on the pink line, only then will you get to the origin. If you start out anywhere else, make the slightest error in measurement and get off the pink line, you end off at infinity. So what's the effect with our governors, our warlike governors, fighting for the tourist trade, willing to spend any amounts of money to match and overmatch what their competitor in the nearby state is spending? The answer is they all lose. They end up, since it's mostly this section of the diagram that makes sense, what happens is they end up all spending an infinity of dollars and nobody gets any more tourists than anybody else. So this is a model of what not to do.